ನಮಸ್ಕಾರ ಮಕ್ಕಳೇ. ಸೊ ಇಂದಿನ ಪುಟದಲ್ಲಿ ನಾವು ಮೆಕ್ಯಾನಿಕ್ಸ್ ಅಂತ ಚಾಪ್ಟರ್ ಓದಿದ್ದೀವಿ. ಅದರಲ್ಲಿ ಬ್ಲಾಕ್ 1 ಎಸ್ಪೆಷಲಿ ಮ್ಯಾಥಮೆಟಿಕಲ್ ಪ್ರಿಲಿಮ್ಸ್ ಅಂದರೆ ಮೆಕ್ಯಾನಿಕ್ಸ್ ಯಾವುದೇ ಸಬ್ಜೆಕ್ಟ್ ಅಂದರೆ ಎಸ್ಪೆಷಲಿ ಫಿಸಿಕ್ಸ್ ಓದಿರುವಾಗ ಅದರ ಥಿಯರಿ ಓದಲೇಬೇಕು. ಅಂದರೆ ಥಿಯರಿ ಪ್ಲಸ್ ಮ್ಯಾಥಮೆಟಿಕಲ್ ಪ್ರೂಫ್ ಇರಲೇಬೇಕು. ಸೊ ಮ್ಯಾಥಮೆಟಿಕಲ್ ಪ್ರೂಫ್ ಅಂದರೆ ಏನು? ಸೊ ಇನ್ ದಿಸ್ ಚಾಪ್ಟರ್ ವಿ ವಿಲ್ ಬಿ ಸ್ಟಡಿಂಗ್ ಅಬೌಟ್ ವೆಕ್ಟರ್ ಆಲ್ಜಿಬ್ರಾ. ಸೊ ಇವತ್ತು ಏನು ಮಾತಾಡ್ತೀನಿ ಅಂದರೆ ಯೂನಿಟ್ 2, ದಟ್ ಇಸ್ ವೆಕ್ಟರ್ ಆಲ್ಜಿಬ್ರಾ 2. ಸೊ ಲಾಸ್ಟ್ ಕ್ಲಾಸ್ ವಿ ಹ್ಯಾಡ್ ಅ ಡಿಸ್ಕಷನ್ ರಿಗಾರ್ಡಿಂಗ್ ವೆಕ್ಟರ್ ಆಲ್ಜಿಬ್ರಾ 1. Further going to vector, what kind of things we are able to explain to this classes. So as previous class we have studied about vector analysis, especially what exactly do you mean by vectors and what is scalars and how to represent in physics. And we have gone through few laws which obey scalars and vectors. So in this chapters we will try to explain the furthermore by using the component form, or maybe for using different going to 3D or 2D. So last class we just went what exactly do you mean by vector and scalar. So in this, as you know, a vector is nothing but a space where you have representation of magnitude and a direction. So specifically speaking, that in a space, like we have a 3-dimension space. If you take a small paper, you have area where you will have only x and y. So if you take a space, you will have x, y, and z. So how do you represent a vector, or how do you calculate representatives of forces which are in spacious? So to define these type of spacious vectors, like a 3-dimension vector or a 2-dimension vector, so these have to be in form of a component, that is along x-axis, along y-axis, and along z-axis. And we will be trying to furthermore explain about what is scalar and what is a vector product using its component form. And also finally we will try to use, let's for a simple is for example velocity is a vector, and how to when you disintegrate or when you integrate or when you differentiate, what you get an acceleration. So velocity is a vector. When you differentiate, you get a vector, that is acceleration. So we will try to explain that derivation or derivatives of vector functions. Next, so what do you like? I already told you that we will be representing the vectors in a 2-dimension space and a 3-dimension space, or maybe in an algebraic representation of vectors by either addition form or subtraction form, or by product, or by scalar vectors. Now, after learning this chapter, what exactly do you learn by this particular chapter, like vector analysis part 2? So you will be able to express the vectors in form of its component. So vector in component sense, there are different types of systems. Okay, so simple system is Cartesian coordinate system, where you will have x, y, and z. And further you'll be studying about the one is cylindrical coordinate system, and then spherical coordinate system. So whenever you have a different function or different vectors applying in, especially in electric field. For example, if you take an electric field and a magnetic field and an electromagnetic field, so usually we state that electromagnetic field is a resultant of electric and magnetic, where electric is in one direction and magnetic field is in other direction, and the mutually perpendicular to both is an electromagnetic wave that is moving, correct? So left is, let's say for example, left is electric wave and right is mutually perpendicular. We consider electric and magnetic, and there is one more line or one more wave or one more axis, or we'll consider where electromagnetic wave is moving. So for this we use this vector analysis, okay, especially in component form. Either we use Cartesian coordinate system, cylindrical coordinate system, or spherical coordinate system, depending upon the situation and the problem. And also we will try to explain the addition and subtraction of in their representative of component form, and also scalar and vector product in the component form, and finally how you exactly differentiate the vector, especially using a function. So first one is vector component in a Cartesian coordinate system. So what exactly is a vector component in a Cartesian coordinate system? For example, you have studied in your previous class, or maybe in your school, where in your degree or diploma, like you will have three types of system, where you have x-axis, y-axis, and z-axis. So this is a reference system or coordinate system. like we already gone through graph chapter in mathematics. So from there also you can try to picturize what is x-axis and what is y-axis. So if you take x-axis and y-axis, it is only a two-dimensional space. It is only a two-dimensional space. In right side, I'm showing you that is a three-dimensional space where z-axis also comes into picture, where these three axes are mutually perpendicular to each other, And in previous class, I have just told you about what exactly is a unit vector and how I represent a vector in form of a unit vector. Unit vector is nothing but it specifies the direction of that particular vector. So in this picture, where you have x-axis and y-axis, where I is nothing but a unit vector. Okay, a unit vector. For example, if a force is moving along the x-axis, then I can be the unit vector along x-axis, and j is the unit vector along y-axis. So it is taken as I, j, and k are the unit vectors along the respective axis. So I is the unit vector along x-axis, and j is the unit vector along y-axis, and similarly k is the unit vector along z-axis. So I cap. So instead of writing I arrow on the top, we just replace the arrow with the cap. So that means it represents the unit vector. So this is a simple coordinate system. This is called as Cartesian coordinate system, which involves I, j, k, x, y, and z. So we'll just limit our discussion in today's discussion only with the Cartesian coordinate system, and further we'll try to explain the different types of systems when you have a let's say while solving a end problem or initial to end problem, like fluid mechanics or maybe electrodynamics further. So how to represent a vector in terms of its component? So in last class, we have seen that we have along x-axis, we have I, and in y-axis, we have along j. J is the unit vector, and I is the unit vector along x-axis, and j is the unit vector along y-axis. Now, if I consider a point P, if you have a x-axis and y-axis, think about a graph. Let's say you have a graph sheet and you have locating some point on the graph sheet. Okay, so to locate a point on the graph sheet, at least you require the that is the projection or the points along x-axis and y-axis. Simple. So let's say consider a point along a point which is specified in the graph sheet. To specify a point in the graph sheet, either you require x, let's say for example x centimeter, or a y centimeter, or anything. Okay, so let's say P, which depends upon x comma y. So P is a point which depends upon x comma y. Now if you try to draw a line, from, especially from the origin, so I'm just sticking my discussion with the origin, and then I will brief out. The vector can also be drawn not only from the origin, it can also be drawn anywhere. Not from the origin, it can be drawn from any point in the plane, okay, or any point in the space. So as of now, I'll just stick my point to the point where the vector starts from the initial, that is 0, 0 origin, and a line is just touching the point P. So this is the length. So this is the length where O is the initial point and the point at which the meets, right? So that is the end point. So the length of this is nothing but the scalar quantity A. The length is nothing but the scalar quantity A, or the magnitude. And if you want to specify the direction, so A vector is the direction which is acting along or from origin to a point P of consideration in a plane. Okay, and if at all you want to have a resolution, if you want to have an inclination, okay, so with respect to x-axis, you either can take with respect to axis, or you can take either along the y-axis. So for simplicity, we'll try to take along x-axis. That means if you draw a line from the origin or incline, okay, to a point of a considerable point, then if you draw a small inclination, that is theta. Let's say a theta is nothing but the angle formed between x and the resultant vector, or the line you have drawn from the origin to a point which you have considered. Okay, so now I want the if I want the value of along x-axis and y-axis, that means x is equal to how much or y is equal to how much in terms of vector A. Okay, that means then we try to resolve the vectors in form of a component. So just trying to extend the point x and point y, where you have the point P, right? So just draw a line from point P to along perpendicularly to x-axis and perpendicular to y-axis. That means it will become either depending upon the shape, it either gives you a square or a rectangle. Okay, so from that you have two projections along x-axis, that is along x-axis, that the vector's projection will be along x-axis and the vector's projection will be along y-axis. If that is the case, then vector along projected along x-axis will be cos theta. The vector along cross will be cos theta. So why is this cos theta? In simple, you have already studied in your trigonometry in the maybe 10th or maybe +1 or +2. Whenever you have along x-axis, okay, along x-axis, that means there is a form of right angle triangle is formed, correct? A right angle triangle is formed. If you have a right angle triangle, then a trigonometry functions can be applied. A theta along x-axis, that is cos theta is equal to opposite, opposite sin theta is equal to opposite by hypotenuse, and cos theta is equal to adjacent by hypotenuse. Adjacent by hypotenuse. What is the adjacent for this particular theta value? It is x-axis. Okay. What is the opposite? That is projection of along y-axis, that is y. So that's why along ax or along x direction we take it as cos theta, along cos theta. And a cos theta, a is nothing but the projection which is happening due to the result vector along x-axis, along x-axis. So instead of replacing just cos theta with the normal projection is ax divided by uh, a bar, or ax divided by a vector. So that is how we take according to the trigonometry. That is like ax. Ax is nothing but the one of the component of vector a. Ax is equal to, or cos theta is equal to ax divided by a vector. Ax divided by a vector. That is usually, I am just using the trigonometric functions. So cos theta is equal to adjacent side by hypotenuse. Adjacent is nothing but ax, that is a component of along x-axis, and the hypotenuse is a vector. So cos theta is equal to ax divided by a vector. So we just take it as ax is equal to a cos theta. Ax is equal to a cos theta, and replace a cos theta by vector a dot I cap. So that is the resultant I along the vector, along the x-axis. Similarly, when you take along y-axis, that will be sine theta. So that will be sine theta. So ay is equal to, so similarly when you try to write ay, so the ay is nothing but the component along y-axis, that is equal to a sine theta. A is nothing but the length of the particular vector. A sine theta, or sine theta is equal to ay by a. If you try to write in terms of a vector, then or vector or the unit vector, then it will be a vector dot j. A vector dot j. So now you try to add this both ax and ay. Ax and ay. That means you are trying to find the resultant a vector. That is the component along x-axis and component along y-axis. You are just splitting the vector a in terms of its component. So now I'll try to add both the equations like sine theta and cos theta. So finally you get a is equal to ax uh, plus ay, that is equal to ax I cap plus ay j cap. So I and j are the unit vectors along ax and ay. Just replace this ax with a cos theta I cap, and ay is equal to a sin theta and j cap. So this is the resolution or the component form of a vector using Cartesian coordinate system. Okay, a simple coordinate system. So it is very easy, where for example you are starting, let's say you are representing a point in a two-dimensional figure like a graph sheet, and then that represent a vector which is moving from origin to some point. Then you have to resolve this. To resolve this, actually you require theta, that is the inclination. If there is an inclination, then obviously it will be a right angle triangle if you just make a projection of it from y and z. Then using trigonometric functions sin theta and cos theta, then finally you get a is equal to a cos theta I cap. That is the a cos theta is nothing but the projection of the vector a along the x-axis, and then a sin theta is nothing but the projection of the vector A along the y-axis, and I and j are the unit vectors which specifies the direction along x and y. Okay, yes. So once again, I'm repeating, a cos theta is nothing but one of the component of vector A, which is moving along the x-axis, and a sin theta is nothing but it is a second component along y-axis, and j represents the unit vector that is moving along y-axis. Yes. Next comes the magnitude of a vector. So what that is the value, that nothing but the a value. So how to find the a value? So we already know to find the a value, that is in previous class we went through how to find the magnitude of the vectors. Just simplify, that's a dot a square is equal to a vector a dot vector a is equal to, vector a we already know it is a cos theta I cap plus a sin theta j cap. Just simplify it. So after simplifying, cos theta plus sin theta, that is sin square theta plus cos square theta, become 1, and I dot I will become 1, and j dot j will become 1, and I dot j become 0, and j dot I also will become 0, and remaining you get a is equal to square root of ax square plus ay square. So a is equal to ax square and ay square. That means it has only the component, it has only the value of the axis along x-axis and y-axis. Only the what you say, what only the projection, not the angle. Okay, the angle in a sense it doesn't have any direction if you consider the magnitude. Let's say, for example, you want to find the theta value. You want to find theta value or the inclination made by the vector along the x-axis. Okay, so that's very simple. Just divide taking tan theta. Tan theta is nothing but the adjacent side by opposite side. So you have sin theta and cos theta, right? So sin theta and cos theta can be expressed in form of its component. So theta is nothing but tan inverse or ay by ax is equal to tan theta. Okay. So what is ay? Ay is nothing but the projection along x-axis. So you can find the projection along x-axis Theta value comes only when the vector represents in form of an angle with respect to y-axis or z-axis. Okay. So summarizing that, the vector and scalar component of vectors a at an angle theta with x-axis are given as a is equal to ax plus ay, that is equal to ax I cap plus ay j cap. So that you just replace with the projection. Ax is equal to a dot I cap or a cos theta, or ay is equal to a vector dot j cap or a sin theta. So straight away you find the component, that is ax and ay, just writing in terms of a cos theta and a sin theta. If at all the vector is given to you in terms of this, then you have to resolve in terms of component and solve those and substitute in the vector a, that is a is equal to ax plus ay. Okay, fine. Next, uh, if you have okay, so magnitude is also same. So magnitude of a is equal to square root of ax square plus ay square. That is I already told you now. That is if a vector starts from the initial position, that is origin to some point in the plane, then that will be actually the length or the line of sight or the distance from the initial position to the final position. So if you consider in that means initial position and final position, let's say consider it as x2 and x1. For example, we consider if it is in x-axis, and y2 and y1 we consider it as in y-axis. So you can also take in a component form, or you can split in and take the initial and final points also. Similarly, you can write the projection, that is ay and ax, in terms of displacement. That is displacement again depends upon initial and final points. So you can just replace ay and a6 in terms of y2 minus y1 or x2 minus x1. So you can do anything possible. Okay, if at all, okay. Previously I just went across starting with origin O. So obviously in this case x, that is x, maybe x1 will obviously be equal to 0 and y1 will be equal to 0. If you take a similar kind of projection, not starting from the origin O. So here in this picture you can clearly see that the vector a and b is starting from some point. Vector a is also some point and b is also some point in the x and y Cartesian coordinate system, where a is nothing, x1 and y1 specifies specifies the position of a, x2 and y2 specifies the position of b in the plane. So in this case you can just split the x and y. So in the previous case x1 was 0 and y1 was 0. So if we try to split ax, right, so it becomes x2 minus x1 and ay is becomes y2 minus y1 because it is just a displacement. Okay, so displacement depends upon the initial and final points. So just replace with x2 and x1, so you get a magnitude of vector, especially when the vector starts from some point in the within the space and it ends in the void. So theta is similarly, theta is tan inverse ay by x. So this is remains same, ax by ay. So ay by a. Just a representation of a point. Okay, in that case ax is nothing but the component along x-axis, and ay, a small ay suffix ay, is nothing but the component along y-axis, and az is the component along z-axis. If you try to represent in form of a vector, simple, a vector is equal to ax I cap plus ay j cap plus az k cap. So once again I'm repeating, a vector is equal to ax I cap plus ay j cap. So now we will try to resolve in form of a vector components, and we'll find the try magnitude and the direction, or maybe inclination. Magnitude remains same, that is in a two-dimension figure it was a is equal to square root of ax square plus ay square. So but when you come to a three-dimension space, the magnitude of vector a, or the scalar quantity, or the normal length, just a normal length, a is equal to square root of ax square plus ay square plus az square. So az square also comes into picture. So that is the magnitude of vector a is given by ax square plus ay square plus az square. So don't forget, square root of the all things is must. Okay, so now coming to the inclination theta. So here we cannot find angle theta using only x and y axis, because z axis also we are considering. So here we are definitely use cosines of angles. So when you have a unit vectors along x, y, and z direction, then obviously cos theta, that means when, for example, if you consider in this case we consider a vector passing from origin to a point P in the x and y direction, in some, not in x and y direction, in space. If you draw a line from point P to z axis, from point P to x axis, that means drawing the line in a sense, just representing its projection. So when you try to project vectors line along the x-axis, y-axis, and z-axis, the length is nothing but ax, ay, and az, and the angle these form are alpha, beta, and gamma. So in previous case, we just took theta as the angle, which is the form between the inclination of the angle with the x-axis. But here, that particular point, right, that particular vector, when it is make projection along x-axis and y-axis and z-axis, so it will meet along x, y, and z. So that means it will definitely have three angles, which is called as direct cosines like alpha, beta, and gamma. So when you try to explain this direct cosines in terms of these vectors, then along x-axis it will be ax is equal to a cos alpha, ay is equal to a cos beta, same. There it was cos theta, sin theta, right? So here it will be az is equal to cos a cos gamma. So now just try to add this ax I cap to find the final vector. Final vector is nothing but a vector is equal to ax I cap plus ay j cap plus az k cap. Now we'll find the component, each component. Ax is nothing but a cos theta, ay is nothing but a sin theta, a cos beta, and az is a cos gamma. Now we'll try to substitute in the magnitude. Magnitude, we already know it as a is equal to square root of ax square plus ay square plus az square. Substitute ax, ay, and az, you get a common. We'll try to remove a outside. A cos square alpha plus cos square beta plus cos square gamma. So we when you try to remove cos square alpha plus cos square beta and cos square gamma and substitute in terms of 1, so that is nothing but the direct cosines. So where cos square alpha and cos square beta, whatever, it need not be alpha, beta, and gamma, it can be a, b, c, okay. Cos square gamma plus cos square beta plus cos square beta, alpha, beta, gamma is equal to 1, okay. So whether it is alpha, beta, gamma, or a, b, c, d doesn't matter. So what matters is the cos square of a plus cos square of b plus cos square of c is equal to 1. So this is the direct cosines. So substituting this direct cosines in 1, then it remains a square is equal to ax square plus ay square plus az square. So it obviously remains as the magnitude of the vector a. Next, if you want to find the magnitude and the direction when of a vector, not starting from the origin, if the vector is starting from some point and it is ending at some point in the space, in a three-dimensional space, then we already went through that x-axis, x along x and y. You can just write in terms of points like p and q. If you try to represent, p and q are the point in the space. It's not starting from the origin, it's starting from some point and ending in some point. That time when you try to project along x and y and z direction, and we can easily try to put that p has a component x and y, and z, x also has a component q has a component. Like if q is another point in the space, if p is another point in the space, if you try to join them, and if that is a vector or a vector moving along that direction, then what is ax, ay, and az is ax, we already know it as x2 minus x1, ay is equal to y2 minus y1, and az is equal to z2 minus z1, because ax is nothing but the projection along x-axis, and ay is nothing but the projection along y-axis of the vector, and az is nothing but the projection along z-axis, and these values is nothing but the length or just the measurement of the vector along x, y, and z. So when you try to write in terms of points, distance, like x2 minus x1 will become ax, y2 minus y1 will become ay, and z2 minus z1 will become az. So similarly, if you want to find the magnitude of a vector or the length of the vector PQ or vector AB, just write A is equal to square root of AX square plus AY square plus AZ square. And instead of ax square, right, you just replace with x2 minus x1 the whole square plus y2 minus y1 the whole square plus z2 minus z1 the whole square. Okay, a simple. So what will happen is x1, x1, y1, and z1 will obviously be 0 when the vector which starts from, or the tail of the vector starts from the origin. If the vector doesn't start from the origin, then x2 minus x1 and y1, z1 will come into picture. Okay, so that is about the magnitude. Magnitude that we have clearly mentioned about the magnitude and the direction in a two-dimension space. And we have found, especially when vector is represented from the origin to a point P in the space. And also we have seen three-dimension space where we have specified a vector which is starting from the origin to a point P. And also we also have specified that a vector can be specified not only from the origin, it can be specified in any point in the space, and how to find its magnitude and the direction. Okay, yes. Next is position. So in usually when we talk about position vector or the displacement vector, because displacement is a obviously displacement is a vector quantity, correct? And position vector or displacement in a Cartesian coordinate system. When you try to represent a vector in a Cartesian coordinate system along x, y, and z direction, we consider a point P. Point P depends upon x, y, and z. Point P in a sense, the position of that particular point in the space, it depends upon the location. So how, like for example, geotagging, right? Now some bee is flying or some car is moving on the earth or in a geostationary, and you want to find the location of it. Then you want to find the location of it, obviously you require the x, y, and z axis along this, or maybe latitude or longitude. Okay, simple. So that's why through basically all this stuff like attitude, longitude, everything happens when you have x-axis, y-axis, and z-axis. When you consider these Cartesian coordinates or specific spherical coordinates or cylindrical coordinate system. So as we are discussing that today's class is about Cartesian coordinate system, the position vector or the displacement, that is just replace a with just r. Okay, so just replace a vector with r and ax with x and ay with y and az with z. So then the position vector along the point in the space, especially when the vector starts from the origin to a point P, is r is equal to x I cap plus y j cap plus z k cap. I and y and z are the projections made of the vector along x-axis, y-axis, and z-axis, and I, j, k are the unit vectors along x-axis, y-axis, and z-axis. That means x is a component of vector which is moving along I direction or x direction. Okay, and y is the component of that particular vector which is moving along j direction or z direction. Sorry, k what is that, y direction. And then z is nothing but it is a component along z axis. It is a component along of a vector along the z axis, and k is nothing but a unit vector which specifies the z direction along k. Okay, and magnitude is remains same, so just replacing with the r, a with r. So r is equal to x square plus y square plus z square. Keeping the compass at the center, keeping one of the needle at the compass at the center, and if you try to draw a circle from the origin, and if you specify the radius, when you draw a line, just a line from origin to a point, any point on the circumference, that becomes your position vector. So that becomes your radius. So it is a position vector. Okay, just a simplification. Now, how to represent a null vector when you have components forms? So when you have what do you mean by null vector is when the magnitude is going to 0. Okay, that is nothing but a null vector. So if A is a null vector, if you consider a vector A is a null vector, which is a vector of 0 magnitude, so its component must be obviously equal to 0. That means its projection along x and y and z should also be equal to 0. That means ax is equal to ay is equal to az should obviously be equal to 0. ಮತ್ತೆ ಇವಾಗ equality of vectors. So when you take equality of vectors, so previous discussion, so when can you say that two vectors are equal? So uh, when two vectors are equal, when their values and also their direction, especially their direction need not be a particular direction, especially their magnitudes and the direction should be same. Magnitude and directions must be same. If you consider a vector A that or vector B, uh, to specify two vectors to be equal, we have to consider two vectors, because equality of two vectors we have to consider, right? So that's why we have to consider two vectors. Let's say our consideration is vector A and vector B. If you try to write the vectors A in terms of component, then Ax I cap plus Ay j cap and Az k cap is the component of vector A. And if you consider other vector B, then Bx I cap plus By j cap plus Bz k cap is the components of vector B. They are equal. If for all they want to be equal, then its component or its projection, that is Ax, should be equal to By, and Ay should be equal to By, and Az should be equal to Bz. If and only if Ax is equal to Bx, that means the first component of the first vector, if is equal to the first component of the second vector, and similarly the second component of the first vector and the second component of the second vector, and similarly the third one, if they are equal, then we straightly put that two vectors are equal. So next is subtraction and addition of these vectors, especially in terms of in last class we just studied about addition and subtraction of vectors, but not in form of component. So we'll try to resolve in terms of component also. For example, you take a vector A and vector B in terms of component form. I consider vector A is equal to Ax I cap plus Ay j cap and Az k cap, and B is equal to vector B is equal to a Bx I cap plus By j cap and Bz k cap. Now I try to add this, sorry, or subtract this. Plus 1 2, that is not happens using vectors. So vectors is slightly different. That previous class I already went through. So C vector is equal to A vector plus B vector. If a C vector is equal to A vector plus B vector, or some other D vector is equal to A vector minus B vector, if that happens, then try to resolve in its component. Just replace A and B with its component. That if you try to replace its component, then obviously you have to get their directions, that is I, J and K. So consider C is equal to vector A plus vector B. You're adding A and B, sorry, vector A and vector B. Now how do you add vector A and vector B in component form? Just split it. Ax plus Ay, sorry, Ax I cap plus Ay j cap plus Ax z cap plus bx I cap plus by j cap plus bz k cap. Now I take I as common. So when I take I as common, then I just combine ax plus bx. I take j as common, ay plus by, and k as common, then I take az plus bz. Okay. Now similarly, that is about just adding the components and getting the value. You get the resultant of the both the vectors. That is addition of two vectors. When you try to subtract, similarly, same. If you consider D is some vector and you are trying to subtract A and B, D vector is equal to A vector minus B vector. Similarly, same, AX plus B, AX I cap plus B, AY B cap, AY